I'm not sure if it might everywhere. Okay. Let's go around.
They basically refer to it as method, right? So yeah. Yes, I know. I see that.
You have a nice ball, right? One ball has a roll and roll out. And the all has to say
Yeah. So you have some, I don't know, this is like zeros.
Yeah, sure.
And you basically you have some information locally.
Yeah, for the this how much is
right.
Okay.
Well, why?
Diameter.
Right. So why can't the diameter this? I don't know. I mean.
Yeah. Sure. Exactly. So how can we get this from like the whole thing, right? So the thing about this, I think the example, for example, is a constant. Okay, so we have a lower bound. Okay, and then we will do the definition later.
Yes.
Okay, in this case, we want actually upper bound. Okay, so it's not true.
Right.
This guy was really fitting.
Yes.
Okay, so you are not complete magical.
Yes.
And for this part, you still can use lower bound. Okay, so you get a kind of minimal, but and also flat. And the output, actually in this case, the volume of this complete non-packed magical must be big. So it's a contribution to the mean. Okay, and but we will use this argument direct. So we use his proof. So his proof. So actually, we can, if you use his proof, this guy actually smaller or equal to some constant plus like 1 over maybe this guy or 1. Okay. Let this constant come out. Okay. So you just estimate. I mean, so it's much more detailed. Okay. So this part of your case, if you got a 1 magical pocket below, you got a pocket. Otherwise, means we got a collapsing somewhere. You got a collapsing everywhere. You got a collapsing over here, the diameter goes to infinity, and then so that's quite different.
I wouldn't say difficult, yeah, right now. Right.
I guess I'm
some old results and some new results on Kahler-Ricci flow and how it is related to singularity theory and also birational geometry, more precisely the middle model program, to classify not just projective but also Kahler varieties. First of all, I'll talk about some background. And I'll talk about the case for Kahler surfaces. And then we look at higher dimensional case, which is much more complicated. And finally, I'll just talk about some detail of this so-called analytic middle model program, the Ricci flow. So this is Tian and I proposed this program. And essentially, I also talk about some related program with respect to this for singularities. Now, first of all, let's look at some background. Suppose I have a Kahler manifold. G0 is a Kahler metric. So let's look at the following system, parabolic system, applying the t derivative to the metric, which depends on time, in the negative direction of the Ricci curvature, starting at the initial Kahler metric G0. So this is actually parabolic. And in fact, this is can be reduced to a Monge-Ampere flow, a complex Monge-Ampere flow. So this is, everyone else is talking about elliptic Monge-Ampere equations. So I just take a slightly different approach, looking at the parabolic Monge-Ampere flow with the time direction. Now, one interesting thing, immediately one can find out, this is, of course, a nonlinear parabolic equations. Now let's, since it's Kahler, let's look at the evolution of the Kahler class. All you have to do is just put a bracket there. The Ricci curvature sits in the first class, or the canonical class. So basically, you're running the Kahler class, or the Kahler metric, is evolving in the direction of minus first class, or the canonical class. Well, if you're familiar with algebraic geometry, this is more or less exactly the idea of so-called middle model program with scaling. I don't know who first proposed this one, but this is the one that has been proved. Not the general middle model program, but middle model program with scaling. So this is done by, I guess, Paken, McCurr, and damn, I forgot the name. Burka, Paken, McCurr, and the HK. Is it? Kachiri, ECHF. All right, and also seal independent with a different approach. Okay. Well, this is just a naive observation. We want to make it into a more geometric approach. So obviously, if you're looking at a Calabi-Yau manifold, then you see that the Kahler class is not moving at all. And in fact, by Huaidong-Tao's result, the flow always converges. converges to Ricci flat Kahler metric. Right? Always converges in the same class. If the first chain class is negative, same result, except that you have to normalize the flow to make sure that the total volume is a fixed bounded number. So both of these works build on the work of Yao's solution to the Kahler-Ricci conjecture as in the 2 series of lectures we've heard today. And the hard part is, of course, the C1 is positive. And again, you want to renormalize it because it shrinks. So you have to renormalize such that this is total volume is equal to 1. And then you ask what happens. And we know that recently this is related to the Tian-Yao-Donaldson conjecture relating K-Einstein metric to certain algebraic stability. More interestingly, using Donaldson's work, also Tian, I guess, there's a couple of different teams. For example, the first one I think is Tian and Jian. And then they prove for the dimension 3 case, you always converge. And forget about the stability. I'm not a big fan of stability notion. And you can forget about stability, just look at the Ricci flow. It's not something, it's better. And it always converges to either Einstein or a soliton. Dimension less than or equal to 3. In general case, this is 2 years ago it was claimed by Chan and Wang for the complex case. And more recently, Bamler proved for the real case. This is so-called Hamilton-Tan conjecture. In order to finally apply this to the Tian-Yao-Donaldson conjecture, again, you still have to go back to the Donaldson-Song's work. Anyway, this is some background. What I'm interested is in the case, well, look at these 3 cases. The first chain class or the canonical line bundle always have a sign. And my goal is to look at the case if the first chain class is not definite. Not even strictly definite, what happens? And turns out that if it's not strictly definite, these 3 cases are not going to hold. And you're going to have either finite time singularities or long time singularities. So the most interesting thing is to understand the formation of singularities for this problem. All right? And our goal is to show basically algebraic geometry analysis. When I say analysis, includes PD and also certain L2 analysis, complex analysis, and also Riemannian geometry. We want to show actually singularities in terms of classifications. These 3 guys come up together. So this is basically a romance of 3 kingdoms. We want to see how everything's connected through the Ricci flow. All right, let me first talk about dimension 2. Well, we all know that the classification for complex surfaces is almost complete, possibly just except for type 7. But at least for Kahler surfaces, it's all done. So let's look at a new type of classification using the Ricci flow or using canonical metrics. So now we always look at, let me call it X. This is a Kahler surface. Okay. And I'm going to run the flow. Apply the Kahler-Ricci flow to this initial manifold. And the natural question is, what's going to happen? Well, first of all, if this Kahler surface does not have definite Fortune class, you're now going to have long-time existence. And somewhere the flow has to stop. And now you want to understand what happens at this bad time, and how can we go through this bad time. I think probably initially this was studied in mean curvature flow, and also kind of proposed by Kalman in his geometrization conjecture, solution to geometrization using the Ricci flow. The idea is construct a canonical surgery by the PD through the singular time. Now let's write down the theorem. This is an old theorem, mine with the Ben Weinkoff. Probably 2010, 2011. Well, there exists a finite many unique sequence of time. Let's say 0 is equal to t0, t1, t2, tm plus 1, less than or equal to infinity. So the last time could be infinity. That means you have long-time existence. And also a sequence x0 to x1 to x2 to xn. So this is just, everyone is a blow-down map. Disjoint -1 curves. Well, what are -1 curves? They are homomorphic S2 with self-intersection number equal to -1. So there exists a sequence of time and a sequence of manifolds. But these manifolds surfaces are related by blowing down one by one through the -1 curves. And also you have solutions, smooth solutions. Of the Kahler satisfies dg by dt equal to minus. So xi cross ti to ti plus 1. Okay. So between two bad times, there's a smooth Ricci flow on the surfaces. Okay. Here I is between 0, 1 to.
Excuse me, can it happen that two minus curve blow down on the same time?
They're always separate. They're disjoint. So it's possible you can blow down distinct.
So you mean there is such a Ricci flow, such that it realizes that
It's actually not such, it's unique. So there's no always existence in
We started from this that the solution is unique afterwards.
The solution is always unique. So I'll tell you the story. So here, I'm just telling you there exists a smooth flow between two singular time, not at the singular time, right? But then the conclusion is, there exists such that, right? First of all, when time approaches the singular time, it's actually a smooth convergence to some, let's say, I plus 1, let's see, ti plus 1, on x minus di. Well, this is xi. this is ixi plus 1. Let's say you just flow down one divisor, minus 1 curve di to a point. So the flow basically converges outside di smoothly at the singular time as t tends to ti plus 1 from the left. Okay. So you always have smooth convergence outside these bad minus 1 curves. Now, this is only a local regularity. For us, we need to understand the global geometry or global regularity for the metric. So that's the second conclusion, which says, well, since you converge outside this divisor di, let's take a metric completion. Ti plus 1. Let me take a metric completion, because the metric outside di or outside this point is a smooth metric. So you can basically take a metric completion. And the metric completion is homomorphic to the next surface, xi plus 1, with a metric there, a mesh.
Homeomorphic or isometric?
It's homeomorphic. But then, since it's homeomorphic, there's only different by 1 point. Basically, that says you take a metric completion, all you have to do is just put 1 point there. So it's homeomorphic, and then outside that point, it's bihomomorphic. It's bihomomorphic outside the point or the divisor, and globally, it's homeomorphic. And also, as time tends to the singular time from the left, it converges in Gromov-Hausdorff distance to the metric completion. I guess Gromov-Hausdorff convergent distance is already discussed by Professor Johnson in his lecture, first lecture. So basically, this is the intrinsic limit. This is the extrinsic limit, because you look at the local convergence limit and you take the metric completion. And this is the global geometric limit from the flow. And these two are the same. Furthermore, it smooths out the flow, because what happens is that you look at the flow as t tends to a singular time. Everywhere else converges nicely and smoothly, but this one is very bad. So in fact, you're going to have some singularity here. This limiting metric space has an isolated singularity. But then the last statement says that it smooths out. So the flow immediately becomes smooth. You connect with the next flow. And it's a smooth point. And in fact, when you go back in T, it's again in Gromov-Hausdorff distance convergence. And also, the convergence is smooth outside this 1 point.
This is also blow down.
No blow down, because here you have the next surface, but you just metrically you have a singularity. You run the flow, the metric singularity is gone. It's smoothed out. It's like a heat equation. You have initial data might be singular, but you run the heat equation, the solution becomes smoothed out, smooth right away.
But you have a morphism between.
Outside it's bihomomorphic. So if you
Outside, okay.
yes, outside. So if I'm not gonna, because we're going to write down, it has to be. It's going to be very long. So basically, it says you have the new the next solution of the Ricci flow. But you take time to go back from the right, and it converges in Gromov-Hausdorff stance to the same person. So that,
But isn't this maybe a stupid equation? Is also roll down, no?
no flow down, because
If
there's
you
no
make
-1 curve.
time go,
No, it's not. It's gonna be sitting on the same Kahler surface, because you already blow down the -1 curve to a point, so you can flow it for some time without changing the topology of the manifold at all. It's not
but
blown down.
outside, this
Outside it's smooth.
mosaic equal.
Outside it's smoothly deformation. But here it's not smooth. Here, because you have a singularity, so the flow basically smooth out the singularity, just like what heat equation has.
May I ask you about terminology? When you say completion, do you mean the limits along geodesics?
Well, because you look, without the metric completion, this is a metric space.
Yeah, I'm asking what is a metric completion?
Metric completion means that given any 2 point in just any space, you can look at a metric completion. Once you have a space with a metric, you can always take the unique metric completion. This is a point set topology. Any set with a metric,
Yeah,
you can always
I'm
do.
not an expert in the area, I'm just asking what is metric completion?
Metric completion is that you want to add, you want to take any Cauchy sequence of any sequence of point which is a Cauchy in terms of distance, the Cauchy sequence, you make it into a new point as an equivalent class.
Limits of geodesics.
So yeah, now you can't say it's geodesic because in general you might not even have a geodesic. So in this case, you take 1 point, for example, the metric completion of puncture disk, the Euclidean metric is the whole disk, because you take the Cauchy sequence with respect to the metric, it has a limit. Even though there's no point, metric completion means that you identify any Cauchy sequence of the new point. That's just the metric completion. You add boundary points.
Just to make it clear, is it true that in the second line, this space without this curve directionally exists the metric space, such that the result space just removes a point from
I
one.
can't hear you.
So, I mean, I just wanted to ask if in this second line, in your particular case, not in general case of metric completion, right? But in your particular case, you just have some nice metric space and you remove another metric space, so that if you remove a point from the metric space, what you get is this thing without.
That's right, you just take 1 point away, that's exactly before the metric
And
completion.
that thing on the right is actually something nice, right? Not just.
You don't know if it's nice. I only know it's homeomorphic. I can't say it's nice. So in fact, you have to do a lot more analysis to understand the metric singularity. So this is dimension 2. Now let's. So basically, it tells you that given any Kahler surface, you run the flow. It gives you more or less. Start with any surface x0. This picture tells you that if it blows down, all the -1 curves on it, depending on the initial gravity. And eventually, if the last time is infinite, that means you have long time existence. It breaks down into 2 cases. If the Kahler dimension is 2, the limiting case is basically orbifold Kahler-Einstein metric on a general type surface, minimal general type surface, canonical model. So basically, you contract -2 curves. This is also in Gromov-Hausdorff distance, and this first down proved by this myself and Weinkoff. And also, more generally, in dimension 3, it's proved by Tian and John. The first proof is dimension 2 case. If the Kahler dimension is equal to 1, this is very similar to the collapsing of Tarabi of manifolds. A little bit like this SYZ picture. So I'll tell you what's the slight difference there. Why it's actually fundamental difference there. So what happens is that this tells you that the initial or the final surface is elliptic surface over some Riemann surface. But there might be some singular fiber. The fibers are torus, generic fiber, smooth torus, but the complex structure is changing. And you might have seen pinched torus at double point. The generic singular fiber is a pinched torus. That means given a torus, you pinch one cycle, and you get rational curve. In this case, this is proved a while ago, 2010. The flow converges weakly. Now, we still don't know if it's going to converge globally, like what Marfan says. It collapses to a canonical metric on the base, on the canonical model, where the limiting metric on the canonical model satisfies a twisted K-Einstein equation. Right? So it's almost like Einstein, except that you have a correction term by the Weil-Petersen metric, because you have on the fiber you have change of variation of complex structure of Kahler-Ricci 2 torus, and of course you have a moduli there. On the modular space of Kahler-Ricci manifolds, you have Weil-Petersen metric using homomorphic volume form, and this comes from curvature of the moduli of Kahler-Ricci space. So this is indeed the degeneration of the Kahler-Ricci manifolds of fiber space. And the limiting metric sits on the canonical model. It's not going to be on the surface. It's going to be on Riemann surface. It's a collapse. And if the singular time is finite, which means the flow has to stop in finite time. You don't have long time existence. There are two cases. Either the original surface is a root surface, or it's finite. So in this case, most likely you get finite time extinction. The flow just becomes to a point. In the root surface case, for example, you consider P1 plus a hypotenuse curve. The P1 vibration, the P1 fiber bundle is going to collapse all the P1. You have a Riemann surface. So
how about the case when the Kahler dimension is 0?
Kahler dimension is 0, you're not going to move at all. It's just the Yau's case, because C1 is 0. So it converges exponentially fast, smoothly to a Ricci-flat Kahler metric in the initial Kahler class. So that's it's not easy. It's from today's point of view, it's relatively this classical case.
Sir, same question. So if you take a K3 surface and blow up one point, then what happens?
You blow down.
First,
You blow down first, and then it converges to smooth. Just like the picture is that you continuously using.
so this Tm plus 1 will be infinity.
This would be infinity. So I didn't add the Kahler dimension equal to 0. So you just do K3 surface, you blow one point, you have one singular time. Blow down the -1 curve, and you have long time existence, and everything behaves nice and becomes Kahler-Ricci metric. So this is dimension 2. More or less, it's quite clear, even though it's not. It takes lots and lots of work. For example, the hardest thing is to show, for example, these. You don't even know. A priori, you don't even know the diameter width is bounded or not. And that's really a hard problem. When you reach the singularity, you can't control the diameter. You can't control the regularity. Now we want to move to.
Excuse me.
Sorry.
Can you explain 2 points? First of all, why do you blow down curves one by one? How to distinguish which curves is blown down?
Oh, the Kahler.
Depends on metric.
The initial class picks up by itself. You can just run the. You just check the Kahler class.
I understand, but why they're disjoint? Yes.
Why they disjoint? It's because from the Hodge relation.
No, he asks why there are different times. In fact, there are not different times. Sometimes I guess you can simultaneously going down a couple of curves, right?
Yeah, but in this case, you never blow down curves that touch each other. It's always -1 curves disjoint with each other. This is because
so you can on some period of time you can blow up, not blow down, not intersection curves.
you never blow down intersection curve. And in fact, the curves, the blow down curves depend on the initial Kahler class.
Yeah, yeah.
Different Kahler class, you blow down different sequences of -1 curves.
You say, you started saying this is because
Because of Hardy relation, you run the flow by the canonical class. And you check, you always blow down the -1 curve such that the intersection of the -1 curves is equal to 0. You never touch each other. Use the Hardy relation.
Is there any description of that? No, I think there's some like shrinking cone about the positive class in the car that eventually touches the -1 curves.
It's possible you can have two -1 curves intersecting, but in this case it's not.
Is there any explicit dynamics of this shrinking cone in homology?
What do you mean shrinking cone?
Can we interpret this blowing down, these blowdowns as dynamics of some natural cone in homology that shrinks to the positive definite direction in
Well, that's not that complicated. You can just check the cohomology, the class condition. It's actually linear algebra. It's very straightforward.
Yeah, it's just a sequence of straight lines in homology.
So now let's look at the high-dimensional case. Running out of time.
Sorry, one more question. Just to make sure that it's properly understood here. So in this point 2 in your theorem,
Right?
so at the singular time, ti, you on xi minus di, you have somehow two metrics, two smooth metrics.
One smooth metric. Only one smooth metric. You have a flow metric, which is depend on time. And the limit is a smooth metric.
But you can flow from one side and from the other side.
Oh, you mean yes? They coincide. They're the same.
They're the same.
They're the same. Yeah, exactly. So everything's outside. It's smoothly.
So outside it's the same.
It's outside the same, but the Gromov-Foster limit is again also the same. Everything's the same at the singular time. But if you take Gromov-Foster limit, they're also the same. Now let's look at a high-dimensional case, which is more complicated. Let me just give you one example. Because in high-dimensional case in birational geometry, you cannot just do contraction. You might have flips. So we really have to do flips here. Let's look at this case. It's got the number wrong, so I have to make sure I got it right. So you look at this vector bundle over Pn. Of course, you switch. And this is the total space. You have a vector bundle of rank n plus 1 over Pn. Here, you just swap n and m. Right? So it's just a bunch of, it's a direct sum of -1 bundle over Pn, O minus 1. And the total dimension for these two manifolds are the same, which is equal to m plus n plus 1. And now the interesting thing is that you can make the contraction of the zero section. The zero section is pretty bad. It turns out that you contract the zero section, you get the same guy. This is singular. In general, it's very, very singular. It's not Q factorial. So basically, you cannot really define canonical class on it. That's very bad. The canonical class is not a Q Cartesian divisor. But if m is less, to make sure, is less than n, less than 1, then you have a flip. Okay, so basically you contract Pn. You contract the zero section, which is Pn. Here you contract Pn. You get a singular point, isolated singular point of y, and this is flip. flip. And the flip always has a direction, because here the canonical class with this map is negative, which means on this side this is bottom. On this side, canonical class is positive. So basically, the Ricci flow, if you look at the equation, it involves in the minus Ricci direction, which means if the Ricci is positive, or if the first Chen class is positive, you have to shrink it. That's why the Ricci flow shrinks a sphere into a point. If it's positive, if there's something positively curved inside the manifold, you have to pinch it. And in this case, you get a singularity, so the flip keeps going and you resolve the singularity in the other direction. Go up here. This is called the flip. So it turns out the Ricci flow is doing the same thing as before in these cases. So I haven't written it up. Well, I didn't have half of the theory before. So let me just focus on this example. In general, you can do lots and lots of huge family, any toric family of this type of local toric flips. So what happens is that, let me just draw the picture. Suppose you have n-dimensional projective manifold. There's a pk here, a projective space submanifold of dimension k is less than n. Well, suppose the normal bundle of pk in X is O minus 1 pk and minus k. Suppose that you can actually do more than that. You can just direct some with different weights. Suppose the normal bundle is very negative, but not too negative. And of course you can do a flip. This is p and minus k. So here I have to assume k is not big enough. K is greater than 1, less than, n minus k. Let's just have to calculate this. K is greater than n minus k minus 1. So k is probably 2k is less than n plus 1 minus 1. Suppose k is not big enough. You have a flip. You basically, if you draw the picture, I should repeat, because flip means that you switch by 90 degrees.
You should add 1 at the left-hand side or subtract it.
It should be n minus k minus 1.
Huh?
N minus k minus 1 on the right hand side.
K minus 1.
Here plus.
But I want to make it sure that this is n, I have to add plus 1, right? So n minus k minus 1 is less than k. Yeah, 2k is greater than n minus 1 sign. Right. Now, then what happens to the Ricci flow? So the flow goes like this. Again, you can do the contraction. This is x minus before the singular time. This is after the singular time. And as t tends to the singular time, this is the flip contraction model. As t tends to the singular time from the left, same behavior happens for this. The flow converges smoothly outside this piece of pk to y outside the isolated singularity. and the metric completion is homeomorphic to the algebraic contraction model. And the convergence is in Gromov-Hausdorff sense. And again, the flow will smooth out the singular theorem as t tends to t plus. Also, converges in Gromov-Hausdorff. This tells you that, in fact, this theorem works for all the toric exceptional locus without assumption of the metric. As long as the Kahler class contracts, does the flip, the Kahler-Ricci flow will do the flip in Gromov-Hausdorff sense. Now, this is only just strong evidence that the Kahler-Ricci flow is doing a good thing. In fact, I want to convince you that singularities are good for us. People are scared of singularities, but in fact, the singularities are doing us a huge favor in the Ricci flow. Well, the idea is that this manifold, in C1 definite case, the manifold always has some nice Einstein metric. But if the first class is not definite, there's no Einstein metric there. So what metric should we look for? Well, I guess just everyone is equal, but I guess some are better looking than the others. And some manifolds, the Einstein manifolds, are better looking than the average manifolds without definite first class. So what are we going to do? Well, you run a Ricci flow, and how can less good looking people become good looking people? You have to work out. You have to do cosmetic surgery. And this is what the Ricci flow does. Right? And it's a canonical surgery. You basically contracts the bad submanifolds. Of course, the trade-off is that you have singularities. But then the flow continues smooth out. Resolve the singularities in a nice way. And this is we basically propose this so-called minimum model with the Ricci flow. So the idea is that you start with a projective or even Kahler variety x0, g0. You can even allow singularities for x0. No problem. Apply the Ricci flow. Now, as t tends to a singular time, well, suppose t is the first singular time. All right. So, the two scenarios, t is finite, which means you have finite time singularity. That means you have to do surgeries. And the surgery is not done by artificial surgeries by cut and paste. Here, everything's run by the PD itself. You don't do any artificial surgery. So there are two cases. Well, first of all, x of gt, it will converge in Gromov-Hausdorff sense to a compact metric space Y. This Y could be very bad. But it turns out that it should be, we conjecture that it should be an algebraic variety or Kahler variety. And then the Ricci flow performs a surgery, a flip. So you have, if necessary, we have to replace Y by X plus using the flip. So basically what the flow does is that the flow converges to a metric space sitting on Y, and then continuously going to X plus through the singular time. This is the first case. This is the first case. The second case, it collapses. this dimension is smaller, which means you're going to collapse a bunch of final fibration on the final fibers. And then you go back and run the flow on Y with the new metric. Everything again is continuous in Gromov-Hausdorff sense. The flow will continue through collapsing. The last case is that it goes to a point. This is the finite extinction. That means Fx is a final variety. And in fact, if you rescale it, you should go back to the singular version of the Hamilton-Tan conjecture. The last case is when T is infinite. Well, in this case, it really depends on the quadratic dimension. If the quadratic dimension is equal to the complex dimension, then the flow should converge to its canonical model with the K-Einstein metric.
This is all conjectures, right?
Conjecture, this is a conjecture. This is conjecture in general. Even with singularities. We can deal with some singularities, but so far. But on the other hand, Jian and I showed that on the singular variety with off-terminal singularities, the Kahler-Ricci flow in terms of plenipotential theory, everything's uniquely determined. The flow can even flow through singularities uniquely.
This Y is smooth, yes?
Y is not smooth, Y is very singular.
Very simple.
It could be very singular.
You said that you can continue.
That's right, but the flow, what Jian and I showed that as long as in the category of birational geometry, as long as in the category of locked terminal singularities, the Kahler-Ricci flow can still be defined, and it's uniquely defined. So the Ricci flow can be defined on singular varieties, not just smooth manifold.
How can you write this flow?
So this is from actually Professor Kowalczy's lecture. What you do is that you resolve the singularity, do the Manche-Ampere flow instead of the Ricci flow. Then you can show that there's a unique flow up there, then you can go down there uniquely. So you have to, this is basically analysis. There's no geometry there, but then it's unique. That tells us that it must be a canonical choice. And in this case, the quadratic dimension is between 0 and n, then the flow collapses. Just like in the elliptic surface. Because you have a Calabi-Yau fibration. The variety is the Calabi-Yau fibration over its canonical model. And the fiber collapses and you have a Peterson metric from the moduli. And in the weak sense, this is already been proved, even in the singular case. It's, this is proved by Jian and I. This is probably, the smooth case is proved by Tsuji. In the singular case, Jian and I proved it. So for the last couple of minutes, I want to go beyond this. And in fact, we think the Ricci flow is the right way to attack the abundance conjecture. But now let me talk about something else, mostly here.
The what conjecture?
Abundance conjecture. And the one, maybe I'll talk about it later. So I'll talk about a little bit about it. So I call this local uniformization conjecture. Well, for Riemann surface, the uniformization theorem basically says with different versions. In terms of differential geometry, it says each Riemann surface you have a constant, without boundary you have a constant curvature metric on it, depending on the genus. Well, in high dimensional, it's not going to be true because not every manifold has K-Einstein metric. If you run the Ricci flow, you have to go through the flips. Now, the interesting about the Ricci flow is that, in fact, for all singularities coming from birational geometry, there is a metric characterization. So this is our conjecture. In dimension 2, we can prove some. Right? Even for flips, we also have some results. But in general, it's very hard, and I think it's going to be very, very useful. What you're going to do is that, if you look at a flip, this is the Ricci flow. The Ricci flow. Let me just say the singular time is equal to 0. I just shift the time back to 0. Before t equal to 0, it's contraction. Afterwards, it's blowing up. The flow resolves the singularity in terms of function of distance. Now, I blow it up. For t less than or equal to 0, I divide the metric by minus t. So the metric becomes very big. It turns out that it converges to sort of the normal bundle of the exception locus of the line. It becomes a shrinking soliton. Let me call it G minus T. For t greater than 0, you can also blow it up.
It's flat along fibers.
Hmm?
Flat along fibers.
Flat, it's not really flat along fibers. Can't say it's flat because it's not Einstein. This is going to be a sub-shrinking Ricci soliton. Let me write it down. Ricci of G minus T is equal to G minus of T plus the Lie derivative by a holomorphic vector field. This one is the opposite sign. Minus, this is called the shrinking soliton. This is the shrinking soliton, this is the expanding soliton. So now the picture is clear. The shrinking Ricci soliton contracts the exception locus. The expanding soliton resolves the singularities. In fact, we conjecture that they will be connected through these two. As t goes to 0, you get a cone on what? The tangent cone on the point, on the singular point of 1. So this tells you that if the conjecture is true, it tells you that all singularities from the minimum model program can be unified as the transition of shrinking and expanding within Ricci solitons. So all algebraic singularities from minimum model program, they have a uniformization. They are all soliton limit. And then you have, once you finish this local uniformization using solitons, you take time to the infinity. You have a global uniformization, which is Einstein on the canonical model. So you have a local theory. And this is extremely useful because if you understand these type of metric, you can go back and understand the topology of the singularity. For example, given a singularity, terminal singularity, isolated singularity, look at the link. The fundamental group of the link is conjectured to be finite. And this is open conjecture. Probably in dimension 3, it's close to solid. But in high dimension, I have no idea. But using this, for example, this singularity comes from Kahler-Ricci variety.
You mean
It's
isolated?
Hmm?
Isolated.
Let's look at the simplest. Even for the isolated singularity, it's not known. But if you know that you have a geometric Ricci flat metric on it, and you have a tangent cone, and the tangent cone is homomorphic to the original, one of the algebraic tangent cone, then you look at the link. The link is positively curved. By Myers' theorem, it tells you that the fundamental group is finite, and you're done. So in fact, you can use this type of analytic tools, Riemannian geometric tools, to go back and to attack algebraic geometry as one application. All right, I'll stop here.
Questions? Comments?
Is it in the style of Perelman's group?
Huh?
Is it in the style of Perelman's group? One character?
Well, I would say if you look at Thurston's geometrization conjecture, it's very much analog to the minimum model program and abundance conjecture. So basically, my personal opinion is that Ricci flow is not going to be so powerful in the real case, beyond dimension 4. But in the Kahler case, I think it's exactly, it should be worked out. In fact, it's going to be Perelman's work. We're trying to incorporate Perelman's work in here as well. So for example, this picture, some of the picture can be realized using, we are writing it up using parameter work.
More questions? So you put the works with Jian, but is there anything new since then?
Well, this theorem is new. Well, for the high-dimensional
It
flat.
is a conjecture, no?
Oh, when Pn more than Pn, if you, for example, if the flip comes from the so-called Mumford complex cobordism, we can all do it. This is the reason we can all do it. For example, any toric kind of a local, the flip locally is a toric flip, then we can always do it. We can basically. We are running it, but we've done some. I've done some special cases before, but now we can do more general families.
Excellent. More questions? Yes, then.